experiences. And so then about a couple of weeks later, he said, okay, we'll have a pivot. And I still don't quite know what a pivot is, but he said you can just talk about your experiences. So that's what I'm going to do. I'll start at the beginning and carry on to where I am now. So first of all, I should introduce myself. I'm Jayant Murthy. I'm a senior professor at the Indian Institute of Astrophysics. I got my PhD from Johns Hopkins University in 1987. I worked for 2 years at Goddard Space Flight Center as a National Research Council fellow, and went back to Hopkins for another 10 years as a research scientist. And I joined the Indian Institute of Astrophysics in about the turn of this century, in about 2000. So I'll go back over all of that again. But let me start with what got me into science in the first place. So that would be, I remember the Apollo 8 astronauts going around the moon, but just barely. That was 1968. So what I do remember well is Neil Armstrong landing on the moon, 1969. And so I remember watching it we had a tiny 11-inch black and white TV, and we saw Neil Armstrong step out on the moon. We listened to the broadcasts. And of course, I'd always been interested in science from the time I was about 6 or 7. But then I guess this triggered an interest in space science for me. Now, over the next few years, my parents, they wanted me to go into medicine. My mother wanted me to be an engineer. My father wanted me to go into medicine. And I knew I didn't want to do medicine. It's kind of boring. So but I did start out in biology. I went to Hopkins first in 1977 as an undergraduate. And I started out in biology. And then after about a year, what you had to do in those days in biology was you had to take organic chemistry. And perhaps this is still true. And I just got tired of Latin names, and I didn't want to take organic chemistry. And I was always taking the more advanced physics courses, so I went into physics. I didn't tell my parents for a year. But I mean, this was the U.S., and so you had a lot of freedom to do what you wanted. So then the next time I went home, I said, by the way, I've switched from biology to physics. And they weren't very happy about it, but anyway. So when I graduated as an undergraduate in 1981, and by the way, I don't have a BSc. Johns Hopkins is the oldest university in the country, in the U.S. It started in 1876, and so they give a BA. They don't give a BSc. So I have a Bachelor of Arts and I have a Master of Arts in physics. So I'm not actually sure if I can get a job in an Indian university because they need an MSc and I don't have an MSc. Anyway, fortunately, IA didn't ask me and I didn't tell them. So maybe I'm okay. So then in 1981, when I got my when I just finishing my bachelor's, I was looking around for a place to do graduate school, and I always knew that I wanted to get a PhD. I don't know why, but I always knew I was going to get a PhD. There was no question of leaving after a bachelor's or anything like that. My only option, I didn't have a plan B. Plan A was to get a PhD. And so I was looking around for places to go, and 1981 was when the Space Telescope went to Johns Hopkins. And so I thought that it would be a good time to work with the Space Telescope. And so I stayed on at Hopkins. And I mean, normally you shouldn't do that. Normally you should go somewhere else. But I thought Space Telescope was coming, so I thought it was a good thing to do. It turned out that the Space Telescope, for many reasons, had a lot of delays. And when they came to Hopkins, what the first years, all the first year students were put in one big hall, about the same size as this hall, There were about 28 of us here, long tables. And as soon as Space Telescope came, we were all kicked out. That room was given over to Space Telescope, and we were dispersed over the building. Now, the building where we were at the time, that was Roland Hall, and that was after Henry Roland, who was one of the best-known physicists of the turn of the 20th century. In fact, my advisor, Dick Henry, he still has Roland's old desk. So we were kicked out into all the old rooms there. I was sent down to the basement. Now, as you know, the Cold War was a big thing. Not when I went, but not that much longer, not that much earlier. And when I went there, I was sent to the basement, which was actually the bomb shelter. So they had these big doors that you were supposed to slam shut in case of air raid. And I guess you would come out to a nuclear wasteland and live happily ever after. But anyway, that's where I was. The office where I was also the junk room. So I had a space. I was sharing with 2 other people. And in the room behind me was where all the junk of 100 years of physics labs were put. So it was an interesting place. Now, so because Space Telescope took so much time, and because there was not much work for students to do at the beginning, it turns out that I didn't actually get to work with the early part of the Space Telescope anyway. So in 81, I guess, 82 or 83, after I got my master's, I decided to start work in experimental astrophysics. Johns Hopkins was one of the 3 or 4 places that had an active sounding rocket program. And specifically, they were one of the top places in the country in ultraviolet astronomy. Now, you'll ask, why ultraviolet astronomy? When NASA decided to go into astronomy, now, NASA has always had a strong astronomy component. And I think the reason for this is because they realized that astronomers, scientists, are the people who push the boundaries. Very often, if you want to put up a communication satellite, you just want incrementally changes. You don't want to have that paradigm shift. Astronomers are the people who always want to push the boundaries. If the spacecraft engineers will give you 1 arcsecond pointing, the astronomers want 1/10 of an arcsecond pointing. If the spacecraft engineers will give you a 50-centimeter mirror, astronomers want a 5-meter mirror. So the astronomers push the boundaries, and that's where you make the major advances. Otherwise, you're satisfied with just getting a couple more transponders on, or getting 10% increases in efficiency. So NASA has always had this strong program. Now, when they started getting into astronomy, there was a bit of a tug of war between X-ray astronomy and UV astronomy. And they decided that UV astronomy was the way to go because UV is not so far from the visible. And so they thought that UV was a good place for all the optical astronomers to get they would be comfortable working in the UV. And also the UV is where much of the fundamental science is. If you look at all of the interesting astronomical lines, if you look at water, if you look at hydrogen, if you look at oxygen, a lot of those lines are in the ultraviolet. And so it's a good place to do science. And so they felt that with relatively minor improvements in technology, or with relatively modest technology, they could make good science gains in the ultraviolet. And so they put a lot of money, a lot of effort into ultraviolet astronomy. And Johns Hopkins, starting with Bill Fasty, and then Paul Feldman, Warren Moose, my own advisor, Dick Henry, it was one of the main places for ultraviolet astronomy. So that's where I started. I started a project in '83. And what my project was to work on an experiment for the space shuttle. Now, this was the space shuttle had was to carry all the hopes of NASA with it. It was going to be the one that would make going to suborbital or going to orbital the same as going from New York to London. Everything was going to be taken up by the space shuttle. You wouldn't have any need for rockets anymore because the space shuttle would be just like a plane, take you up, bring you down, and the cost might be $100 per kg. So we were caught in that cycle, and what the goal was eventually to move all astronomers over to the space shuttle. So they had something that they called a getaway special, and that was a gas can, and that was a can about 1.5 meters in height, maybe about 75 centimeters in diameter, and you were supposed to put experiments in there. So like on the space shuttle, many of the experiments were ants in space and how plants grow and all that kind of useless stuff. But they decided that we were going to be the test bed for astronomy. So at Hopkins and at Berkeley, there had been a long-standing controversy about what the sky looked like. And so Charlie Pellerin, who was the head of the Getaway Special program at the time, he said, okay, why don't we fly these two guys together? These two guys, they fly rockets all the time. They never agree. So we'll make them fly at the same time, looking at the same places, and we'll see if they agree. And so that was what the gas can was. And we were supposed to fly in I guess, 84, and we did it pretty close. We flew in, I think it was 86. And we were the last shuttle before the Challenger. So now the Challenger accident was 1986, and I was on the basketball court. It was at about, I guess, 12:30 or 1. So normally we played basketball 3 days. I was a gym rat, played basketball 3 days a week, ultimate frisbee 3 days a week. Sunday was my day off. And so I was on the basketball court, and one of the students came out and he said the space shuttle exploded. So we were all playing basketball. None of us heard him properly, and so we kept on playing. And then at 2:30, our basketball games were a good 2.5 hours. So and this was in the days before an air-conditioned gym. So we would play in 45 degrees, 50 degrees. It was pretty wearing. So we went back to so when I went back to the department, then everyone was quiet. And it was a major disaster for astronomy. I was graduating just about that time in 86. And before the shuttle exploded, there were something like 10, 15 jobs a month. After the shuttle, for space science, after the shuttle exploded, there was maybe one job a year. So I had a job lined up at Northwestern to work on the Compton Gamma Ray Observatory. And when the shuttle exploded, everything dried up. No money at all. It was almost like Trump was there. So then our payload had already been delayed by 2 years, our shuttle payload. And so I had told my advisor that I've been here for whatever it was, 3 years. I think it's time I left. And so I picked up another project and I did my thesis on something else. But then we got data from our shuttle program. And so I stayed on at Hopkins for another year to write up that data. And it turns out that we still didn't agree with the UCB guys. So that's the way that goes. So then in 86, as I was saying, the jobs really dried up. And so I was looking around pretty desperately for jobs. And fortunately, I got one of these National Academy of Sciences fellowships at Goddard. So I went to Goddard for 2 years. The guy I was going to work for, he actually left before I joined. So it was a little bit of I was left almost alone at Goddard for 2 years. And it's actually not a good thing, because just after you finish your PhD, you're not really ready to do anything new. So I was left alone for 2 years, and I did some things, but it was a pretty inefficient time. And then I didn't like Goddard at all. In the days when I was there, this was 88 and 89. In the days I was there, it was actually 89 and 90. It was still a fairly open place. One time I had to give my car for servicing. Goddard, by the way, it's in Hopkins is right in the middle of the city. And so I always lived right next to this campus, and I would walk to the campus. It was a pretty unsafe area. Where the areas where I lived, there were drug gangs just one street over from where I lived. It was not uncommon for us to hear gunshots. But you know, I was 21, 22, 23, so I would happily walk back and forth at midnight. It was perhaps not the smartest thing to do, but I survived. And so when I went to Goddard, Goddard is out in the middle of the suburbs. And in American suburbs, you can't manage without a car. There's absolutely no place that you can live close to Goddard without a car. So I had a car, and I would drive in. And once I gave my car to servicing, and I left my Goddard badge in the car. And so now I don't believe they would let you in. But in those days, they were laid back. I went to the security guard, and he said, okay, I'll write your name down on my book. If you ever do it again, I'll blackball you. And then he let me in. We had a time when some guy forgot his badge and he climbed over the fence. The security chased him for a while, but they didn't catch him. So I was in building 21 at Goddard. And Goddard, for those of you who may not know, it's really the main science center of NASA. Ames has a fairly good science program, but Goddard is where at least all the ultraviolet astronomy, the gamma ray astronomy, the X-ray astronomy, that all comes out of Goddard. And Building 21 was where it was the Science Directorate, Code 680, and that's where the science was done. Now, when I was at Goddard, because I was a National Research Council fellow, we were not really part of that civil service establishment. And so NASA had all sorts of rules. And you couldn't have a civil service guy sit with a contractor. They didn't want to hire too many civil service people because, of course, once you hire a government employee, you can't get rid of them. So they, I mean, it's not quite true, but pretty close. So they didn't want to hire people for all these spacecraft projects. So they hired contractors. But contractors can't share offices with government employees. So because we were sort of loose cannons, they shifted us around from here to there. When I joined Goddard, you could still smoke in your office. So that was in 1989. And so once I was put in with a smoker, which was a terrible time for me. Within a few months, they allowed smoking only in, the way the building was that you had the main building, and then you had an airlock, and then you had the outside. So you had double doors. And so then they allowed smoking in that little place between the doors. So you can imagine 5 people sitting in there smoking. And that was, you had to hold your breath when you went out. Then after that, they moved everyone outside, and now they don't allow smoking anywhere on campus, which is true at Hopkins also. They used to allow smoking in the offices. Now they don't allow smoking anywhere on campus. So we were moved around. So I had like 4 different offices at Goddard. And then, I mean, there were all sorts of things at Goddard that bothered me. Once they ran out of paper in August, and that they couldn't buy any new paper until October because that was the financial half year or whatever. So we all had to walk around with our own stacks of paper for 3 months. So after Goddard, I went back to Hopkins. And what I did there was we were working on a project called Hubie. Now, NASA has these Explorer programs, and you have Explorer programs of different classes. You have small explorers, medium explorers, and then whatever called discovery class missions. So we were working on a project for a small explorer, and then for a medium explorer. The way it works is that the only difference between them is the budget. So we would look at the budget, and we would change our budget to match whatever they asked for. Same proposal. If they asked for $30 million, we'd put in a budget for $30 million. If they asked for $80 million, we would put in a budget for $80 million. And the way that these proposals were always done is that you tie up with some major contractor, aerospace contractor. So we would tie up, many times we tied up with Ball Aerospace. Many times we did it with APL, the Applied Physics Lab. Now all of these guys, they depend on contracts these contracts, the military industrial complex. So they depend on these spacecraft contracts for their survival. So they had a budget dedicated to proposals. So they would have a team who would work with you in putting together a proposal. So you would work on the science, you would work on the science instrument, but this team would put together the spacecraft, they would put together whatever engineering you needed on the instrument. They would make sure everything worked. And then finally you would get a nice glossy proposal, 2-page spiral bound with glossy photographs, fold out pages and all, a very professional job. And you would submit it to NASA. And then NASA would take their time, they would think about it, and then they would come back and tell you whether you were accepted or not. So in 1990, when I went back to Hopkins, we were selected as one of the options to fly on this mid-size Explorer. The other option was WMAP, the microwave anisotropy probe. And naturally enough, because that was hot right after Kobe, the microwave background, they were the ones who got selected, and we were an alternate program. And then after that, so we didn't get accepted. But then after that, what happened was that I got involved in a ballistic missile defense organization program, BMDO. You may know it better as Star Wars. So this was something that Ronald Reagan did. And what he wanted to do was to shoot down 95% of all incoming Soviet missiles. Right? So you have a lot of Soviet missiles coming in, you shoot down 95% of them, 5% of them still get through, which doesn't do Washington, D.C. or New York or Los Angeles any good, but still you get 95% of them. Now, sometime during the course of this program, this was called, so the program I was on was called the Mid-Course Space Experiment, MSX. And the goal was that you would catch, it was part of where you catch the rockets coming in. You don't shoot them down, but we would catch the rockets coming in. The person who led this program, Steve Price from the Air Force Research Labs near Boston, he had this idea. He was very good at combining astronomy or at selling astronomy to the military. So he would do the astronomy that he wanted, but he would convince the military that this was a good thing for them to do also. And so the way he sold this program to the military was that he said the missiles are going to be coming down, but they have the sky behind them. So you have to know the sky in order to know what doesn't belong there. So that was the idea. There were a bunch of infrared instruments which have done really good science, and there were what I was working on was the UV and visible instruments. The instruments were overly ambitious, and so they didn't get as good science as they could have. I still have all of the data. The data are stored at APL on exabyte tapes, And I still have an entire copy of the data on these digital tapes, exabyte tapes, these 4mm tapes. Unfortunately, my tape reader is now not working, and I know of no way to get the tapes read. So if anyone knows how to get 4mm DAT tapes read, I have 2 terabytes of data sitting on tapes. This was the time when we were still experimenting with data formats. And these tapes seemed great because discs were still expensive. CDs were only 700 megabytes. So it was a great thing to store 4 or 5 gigabytes, 10 gigabytes, 20 gigabytes by the end on these digital tapes. But the tape drive I have is a SCSI drive, and there are no SCSI ports anymore. And I don't know if my tape drive works, and I don't think there's anyone who can read 4mm tapes anymore. So that's the way it goes. They're still sitting in APL, but it took me 3 months to get the data into my tapes, and I just don't want to go through that again. So now I was working on the UV and visible part. Now sometime in the middle of the MSX program, the Russians collapsed. And then now you don't have to get 95% of all incoming Russian missiles anymore. So now what I guess the right term is now they pivoted. And they now said we'll get 100% of all Iranian missiles that come in, which I guess is more realistic, or what is perhaps relevant now is we'll get 100% of all North Korean missiles that are coming in. And so we managed to continue, and it flew. We got data. I have 1 publication from it, but as I said, the data I don't really have a way to look at the data anymore. And what always happens with scientists is that they're always so busy with new things that it's hard to go back and look at something that's 30 years old. 20 years old. So there were a couple of funny things with MSX. The data were classified, but the astronomical data were unclassified from the moment they left the spacecraft. They cut out parts of the data where there were satellites going overhead. So we would have the data. We would have an observation, and they would cut out a part of that observation because there was a satellite overhead. I guess eventually they figured out that you could tell where the satellites were from the parts they cut out, and so they stopped doing that, and they just gave us all the data immediately. We still had to get it cleared before publication, but it was just a formality. So that was the one and only time I've ever worked on a Defense Department project. Now, they had different rules than NASA projects. So in the Defense Department, anytime if there's money left over, they take it back. If there's equipment, they take it back. So the goal with a Defense Department project, you always spend the money as soon as you can. Because once you spent the money, they can't take it back. And in fact, this happened with MSX. I was being paid out of MSX. And then after I was being paid out of MSX, and I had some money to look at Voyager data. Voyager by this time was already out at the edge of the solar system, and so we were looking at Voyager data because we were interested in getting out of the solar system. So anytime you're in the solar system, you see all this light from the sun, zodiacal light, and so on. Further out you go, the less zodiacal light. So Voyager, we looked at data all the way out to 100 AU. I have data out to 100 AU. So that was paying for half my salary. MSX was paying for half my salary. And then suddenly one day, they decide to cancel the program. Other people were hurt much more, were hit much harder than I was. So there were people at APL. One guy was called in and said, I'll leave his name out. So man, what are you doing tomorrow? Where are you going to work tomorrow? And it's quite literally, one day you have a job, next day you don't have a job. So I think I had that month's salary. Next month I didn't have a salary, or I had half my salary because I was paid from Voyager. So then, by that time, we had got the FUSE project, the Far Ultraviolet Spectroscopic Explorer at Hopkins. And they had asked me earlier if I would join them, and I said, no, look, I'm too busy on this. So then I went and said, I need half time on this. And so they said, okay, and I started working on FUSE software. And I wrote about some of the FUSE pipeline. So it's still sitting there. The data from FUSE are still there. And then eventually I shifted over to FUSE full-time. And I was there until just after launch. Now, the launch was in '99. And we were all supposed to go to Goddard for flight tests. And as already by that time, I guess NASA had started getting more stringent. And so they wanted me to fill out a long form to go to NASA as a non-American. And I went and told the FUSE PI, I said, you know, this is such a pain. Do I really have to do this? And he said, no, don't worry about it. And then the next day or a couple of days later, they had the Indian nuclear tests. And then it became impossible for any Indian to go to Goddard anyway. I know of people who had these NRC fellowships, students, and the senior NRC fellowships, senior faculty, their trips were canceled because you just couldn't get, Indians just couldn't go into Goddard. So then I was with FUSE until it launched in 1999. And I left pretty much immediately after it launched, within a couple of months after it launched. It turns out it was I probably should have stayed 6 months longer. They had the first 2 FUSE papers, and those papers have 1,000 citations each. And because I'd left, they forgot to put me on. And by the time I noticed, it was too late. And I told them, I said, why didn't you leave me out? And so they apologized, but that's like 2,000 citations that I don't have. So then what happened was in '99, working on the FUSE software, I decided that I didn't really want to do astronomical software for a career. I didn't want to do software as a career. So then I had an offer from IPAC, from the Infrared Processing Analysis Center at Caltech, and it was to do software for I think for Certif, which is now Spitzer, and I just didn't want to do I didn't want to do full-time software, full-time astronomical software. It's a different mindset. You do software, you don't do science. You just don't have time to do both. So I think I'm going to have to start speaking louder. So I didn't want to do the software, so that was one thing. And then I also had an offer from the SWIFT program, which had just been accepted. And I had an offer to be the optical scientist, the scientist on the optical monitor. And that would actually have been a good thing. But then I was thinking that this is soft money. In the US, you have these soft money positions where you're not tenured. And so that would have been, again, a non-tenured position. And after 10 years on SWIFT, I would again be in the same position, but older. So it turns out that IPAC was actually a permanent position, but it turns out that those permanent positions are less permanent than seemed at the time. So people who joined there at the time have now had to scramble around. But the main reason is that I had been talking to people at IAA about Astrosat. Astrosat was first proposed in, I guess, '88 or '89. And by the time it sort of came into fruition, it was mid-90s. And so Ashok Pati from our institute, I had invited him to Hopkins. He came over, we had a discussion about collaborations. Nothing happened, but then they asked me if I wanted to join IAA to work on Astrosat. And I thought it was a good opportunity. Astrosat should, if it had launched in when it was supposed to, it would have been a major new advance, a big new ultraviolet mission. And I also had a bit of an existential crisis. If you're in the US, you're, no matter how big you are, you're a small fish in a big pond. I felt that if I joined IAA, I might have the chance to make more of an impact. That, there are not so many, there are a lot of astronomers in India, but as far as publishing astronomers, there's not more than 100. So it's a much smaller community, and I thought it was a chance to make an impact in a smaller community. And so I came in September 1999 to IAA, and we were immediately working on Astrosat. Now, the problem is that, so this is where it gets a little bit controversial. So in 1999, when I joined the Astrosat program, there were a few of us working on it. We still had no formal approval from ISRO. And so our institute said, and I think rightly so, they said unless we have a formal approval, we cannot put heavy resources into the project. And so the 3 or the 4 of us, we were struggling to put together the proposal. And we finally did, and the proposal was accepted in 2000. But ISRO, they gave approval and they gave money to TIFR, but they did not give any money to IA. And part of the reason was that they said, we're not convinced that you can do it. But it's almost a chicken and an egg problem. If you say we're not convinced that you can do it, but then you don't give any seed money to start, how are you going to show that you can do it? So we were struggling along like this for 2 or 3 years. In fact, Ramnath Kaushik, who was the director at the time, he even told ISRO, look, why don't you just stay out of it? We'll put in the money for our own payload. But ISRO didn't want to do that. They wanted to keep control. And so finally in 2002 or so, we had I think done a good job. But the ISRO philosophy is different. They don't understand scientists. They're very much, I think it's different. I think it was different in the old days. I think it was different when they started. It was a much more open culture. But certainly since I've come, ISRO has had no appreciation of the way that scientists work, and they have no appreciation of the way science works. And so they wanted to have things done in this specific manner. And they wanted to have things done with people that they trusted. And so in 2002 or 2003, maybe 2002 or 2003, they brought in a project manager. Now, the problem is that when you do this, you're bringing in someone who's already close to retirement. You're trying to do this with people who are, if you're trying to build a space program, you need to do it with people who are in the prime of their career, and you need to constantly bring in new people so that there's a growth. So this is the way the American program started. When it started, everyone was new, but then it grew. They made mistakes. As they made mistakes, then they didn't make the same mistakes twice. The teams grew, so there were larger and larger groups of people. So the rocket program at Johns Hopkins, that's fed much of the current satellite programs in the US, a good 15, 20 people. But if you have someone who's already close to retirement and then you try to do it with retired ISRO engineers, you're just not growing. You may get something done, but you're not growing. And so this I think was a big mistake, and I think it's hurting us now. So then in 2002, the project manager came in, and pretty soon the rest of us found ourselves out. And this is something that I tell my I tell everyone. If I have a problem with one person, maybe it's my fault. If I have a problem with everyone, then maybe I'm the one to blame and not everyone around me. So we all had had our falling out with the project manager. We all left the program. And frankly, I think for me, it was a good thing. So then this was 2002, 2003, and UVIT kept going along. As you know, it flew in 2015, which is way too long for any scientific program. It's okay if you're going out to Pluto. You can't avoid it. Or if you're going to Saturn, again, you can't avoid it. You spend a significant fraction of your scientific life. But for a payload that's going into low Earth orbit, to spend 13 years to spend 13 years or 15 years on that program, the science has already passed you by. The science of 2000 is not the same as the science of 2017. If you're going to Pluto, Pluto is not nothing is going to go to Pluto before you do. So New Horizons, even though it launched in, when was it, 2006 or 7? Even if it launched then, there's nothing going to go to Pluto before it. There's nothing you can do. So that science is not going to change. But for UVIT, Galax had already flown. Galax had flown in 2003, and it had stopped operation in 2010. So the science was already old. So then in 2003, I had been talking with my Israeli collaborators, Noah Brosh at Tel Aviv University, about an opportunity to fly a payload that they already had built on an ISRO satellite. And the people at ISRO, especially Dr. Goel at ISAC, they were very encouraging. Now this was a time when there were a lot of contacts between India and Israel. And Dr. Goel said, he said that we have a lot of commercial contracts, but let's have something that's just a pure science contract. And so we did that. We had a pure science contract. And the way that these things always work is that what happened is that Sharon had come to Delhi to talk to the Prime Minister. And Noah Brosh had managed to get Sharon to talk about Tauvex with the Prime Minister. So Vajpayee at the time. So Vajpayee then asked ISRO, what is this project? And then Kasturirangan, who was the chairman of ISRO at the time, he was going to Israel. And he said, I need a project because I have to sign off on something. Because why are you going to Israel? Well, you go off to Israel to sign off on a project. So the only thing that they had was my project. So then they called me in, and within 2 days they approved everything. And for any of you who worked with ISRO, you know that 2 days is a remarkable period of time for them to approve anything. Normally it's, I was going to say 2 decades, but maybe 2 years. But 2 days, they approved everything. And then it turned out that the Israeli Space Agency got cold feet. So he actually didn't have anything to sign. But then in December of that year, the Israeli science minister came to India. And he came to Bangalore. And this was on Christmas Day of 2003. And so again, they have to have something to sign. So they signed, so they called me in. And I had actually planned, we had a family vacation planned to Delhi. And I said, look, I'm going to Delhi. I said, no, it doesn't matter. You cancel it. We want you here. So they had us there, and we all signed this agreement. And that was 2003. It was supposed to fly in 2005. And then all sorts of problems with the GSLV. And in fact, we had a satellite, and then GSLV-3 blew up. And so they took our satellite. And GSLV-2, I think, sorry. Anyway, one of them. They blew up, and they took our satellite away from us. We were ready to go, and they took the satellite away. And then finally, we were going to go on GSLV-4, and we had a launch readiness review in 2010, January of 2010. 2010. And everyone was happy. We were sitting on the spacecraft. We'd been integrated with the spacecraft. We were sitting there. And then I went to Trivandrum or maybe Calcutta. I think I gave a talk at the planetarium there. And then as soon as I come back, I get a call from the ISAC director, TK Alex. And he said, how would you like to fly on a PSLV instead? I said, no, I'm quite happy where I am. And then it turns out that there were some concerns. And they said it was a weight concern. Our weight hadn't changed. We were the same weight for 10 years. We were already mounted on the spacecraft. The first time I've ever been on a project where after the launch readiness review, you're ready to launch. After the launch readiness review, they took us off. And then they said, oh, they promised me a PSLV. It turned out it never happened. And so finally, we're scientists, we write papers. Noah Brosh and I, we wrote a paper on the failures of Tauvex. And ISRO was very unhappy with me. I got a call from, or actually Siraj Hassan, who was our director at the time, he got a call from TK Alex, and he said, you've got to stop this guy talking. And Siraj, fortunately, he said, well, I can't do that. And I got an official letter from him saying, you're not allowed to talk to the Israelis anymore. And so I sent back an email. I said, I don't work for you. But that was a pretty, ever since then, I've been leery of doing anything with ISRO, just because I don't trust the process there. And so this was, it was taken off in 2010. We tried for 6 months to get it on a PSLV, but it never happened. And now Tauvex is sitting in a museum in Israel. We think that it was a waste of resources. It was something that was ready to go, mounted on the spacecraft. We'd already worked for so much time on it, and it just didn't take off. So then that brings us up to about 2010. Now, as I said, I was reasonably happy. I think I was really upset at the time when I was taken off of Astrosat. I mean, never officially. It was just sort of eased on out. But I think, in retrospect, I think it was a good thing. Because again, working for 10 years, if I had been working on UVIT the whole time, it would have taken up 75% or 100% of my time. And especially the way that, that meetings go for these big projects. You have meetings, and in that meeting you have a bunch of agenda items. And in the next meeting you have the same agenda items, which you then push on to the next meeting. And so you never actually have a meeting in which you accomplish anything. You just have a meeting in which you discuss agenda items. And so, so I think that would have taken up a lot of time. And as it happened, I had a lot of extra time, which I've done in, I give classes around the city. I've had after UVIT and after Tauvex, my paper productivity jumped dramatically. Now then, so the final stage of this journey, it was when we decided to start an MTech PhD program with the University of Calcutta. Before that, our students were all direct PhDs. So most of them were so most of them were science. All of them were science PhDs. No instrumentation at all. But then once we started this program with the University of Calcutta, we started getting these students whose primary focus was astronomical instrumentation. Not science PhDs, but astronomical instrumentation. And so we had to start, the goal was that, the idea was that in the country, we have too many people who are doing theory and not enough people who are working with their hands. So then once we got this program, then we were all looking around for things to do. And this was around the time that the low-cost access to space really started coming into the news. So this was not long before the Strand 1, that mobile phone that was launched by the PSLV, and then PhoneSat by JPL. So these were all coming up then. And this is when I think I had probably my biggest insight, which is just that space, when I started, space was reserved for big institutions. It was reserved for places that had the facilities, the infrastructure to put together these big things. And NASA, ISRO, ESA, these big space agencies. So around this time, around 2010, it started looking like space may be more accessible. This was still before CubeSats, but it was getting easier to go into space. If you can launch a phone into space, a phone you buy off the shelf, if you can launch that into space, then why can't you build your own stuff? And in fact, if you think about it, any country has a space program before they have a car industry, because automobiles have to work in all sorts of conditions. There's millions of automobiles out there, as I found to my cost today. There's millions of automobiles out there, and they work. They work at -40, they work at +50, they just continue to work. If your automobile fails at the rate that rockets fail, you can buy you don't have to have this mystique of space qualified parts, of space expertise. It's possible to do things on a lower level, especially if you're not building a $10 billion spacecraft. If you're building a $10 billion spacecraft or even a $1 billion spacecraft, then a few $1 million spent on components is a small investment. But if you're building a $1 million spacecraft, then maybe you can compromise. Maybe you can go mill standard, or maybe you can go industrial grade. So this is what we're doing. And what we started to do was a balloon program. So rather than start immediately with space, because at that time, this was, I guess, 5 or 6 years ago, that space program still didn't exist. So I went to the director at the time, and I said, let's start this. And he was kind enough to give me some 20 lakhs, well, probably about 10 to 15 lakhs a year. And we started up a balloon program. So this was a major learning process. Approvals in India for anything are not easy. And getting the balloon approvals was a learning process. When we first started getting them, they showed us well, Srijit and my other student Akshita had gone. And when the first time they went to this place in Palace Road, well, near the palace, where the paratrooper regiment place. You get a retinal scan, you get your thumbprint, and you go in, and then they show you these pages, and those pages are marked confidential. And they said you're not allowed to tell anyone. So you're not allowed to tell anyone about the regulations on how to fly balloons. So finally we got it, and a lot of it we got because we're a government institution. And so now we have these balloon approvals that we get. We struggled, or it took us it was a learning experience figuring out where to get balloons from. First we got Chinese balloons that were a little bit larger. We got balloons from Pavan Rubber in Pune. Some of the Chinese balloons that we got had been stitched. Not originally, the rubber had torn, or the latex had torn, and they stitched them back together. So now we stick to Pavan balloons, which is a pretty good supplier. They supply balloons worldwide. A lot of the stuff we did, a lot of the electronics we built failed the first 4 times, 5 times. And so I had, yesterday I met a bunch of kids from RV College. They want to put together a satellite, and they want to do everything for the first time. So I told them, well, maybe I'll get to this later, but I told them you can't do anything without practice. No matter how good you are, the first time you do anything, especially in any stressful environment, it's going to fail. So our balloon payloads failed for all sorts of reasons. One time we had been reusing metal rings, and these balloons, they're 2 kg balloons, but they pull with like 10 kgs of force. And this metal ring snapped because we had been using the same metal ring for 3-4 times. So a learning experience. Now we use new equipment every time. Rope snapped. We went through a cloud. It never occurred to us that if you go through a cloud, you're going to get moisture condensing on all your electronics. So these things happen. The first time we sent something up, it got too cold. We put it in an insulated box. It got too hot. So now we have a box with a hole in it. These are the things you learn. And I believe that without that experience on balloons, I don't believe that we could build the stuff for space that we're building now with any confidence. So now after a little while working on balloons, now we started a lot of it through contacts with random contacts. Some of these conferences that NP had called me to. We met other people. Now we have a fairly good collaboration with PESIT. And so we're putting together something for PISAT 3. We're putting together a small UV payload for PISAT 3. And a lot of what we do, we don't want to be doctrinaire about anything. If it makes sense for us to buy, we buy. My budget is something like 80 lakhs for 3 years. So if it's affordable, I don't want to spend, we're a research institution. It's not my job to build a better mousetrap or build the same mousetrap. What we have to do is we have to do something that finally the way we measure ourselves is by publications. And so our stuff has to be good enough to be published in the international journals. When we go to a conference, we should not be ashamed to talk about what we do. So that's what we do. We're a research organization. Personally, I believe that if we don't do world-class research, there's no point. We have to do research that's comparable to anything else in the world. And because we got in at the early stage of this low-cost revolution, I think that we have an advantage. We are getting in on the stuff that we're building is at the forefront. We present it at conferences, and people are interested in what we're doing. So now we're building something for PISAT 3. We built a small star camera, and again we thought about it, and we said let's build something. We want to do it in stages. We don't want to go to very complex things at the beginning, because you start making mistakes. So we start with simple things. We want to go in stages. So we thought and said, what is a simple thing that we can build? It's just a star camera. But how can we make it better? So what we did is we made a small star camera and a cheap star camera. The first star camera that we built is about 5 lakhs. Main cost of that is because we're using a star 1000 CMOS chip, and that's a space qualified chip that's expensive. But then, what is a star camera? It's just a camera that looks and gets pictures of stars. That's all, a star camera. But really, it's more than that, because what's a star sensor but a star camera? So the way we're selling what I'm interested in is the star camera, looking at the stars. What can you do with a small star camera? Well, not very much. What you can do is if a supernova goes off, you can get it. So you might stare at a patch of the sky, and you look for these transients. You look for supernovae, you look for flare stars, you look for asteroids coming in. So this is what you do with a star camera. But really, what we're trying to reposition it as is a star sensor. All that a star sensor does is it takes pictures of stars, and it converts it. It compares those pictures with a star catalog, and you get a position. And so now the next generation star sensor that we're doing is much smaller. It's about a half U. This current star sensor is about, I guess, 1.5 U. But our next generation star sensor, which we'll have done in a month or two, is a half U, and we're coming in at a total cost of about 2 lakhs. And so you go out into the market and you see if you can buy a star sensor for under 10 lakhs. I think it's difficult. And so we're also saying that we're trying to put it on Team Indus. We're saying that a camera is a camera. We don't have to look at stars. We can look at the moon. We'll take pictures of the moon for you, and we'll do a better job than the commercial star sense cameras that you buy. So this is the sort of stuff we're doing now. The easiest thing to do was a visible star sensor, so that's what we started with. And there is a lot of interest in getting this out into the general market. I had in this kind of small cheap things, because now you open up the market for university students. You don't have to spend 10, 15 lakhs to build something. You can do something for 1 or 2 lakhs. And so now the next things we're doing is now we're doing things that I'm more directly interested in, which is going back to the ultraviolet. We want to build an ultraviolet star camera. It turns out that if you want to build a useful ultraviolet star camera, then you need to put a microchannel plate. You need to do photon counting stuff. It's not just a standard camera. So this adds a level of complexity. But we think that we're developing our own detectors in-house. The UVI, so essentially what we think we can do, UVIT was, conservatively speaking, 40 or 50 crores. We think we can build something that does 60%, 80% of UVIT for under a crore. And that's where we think the market is. That's where we think science is heading. Now, when I had gone to Israel, I guess about 3 weeks ago, we had a conference on UV astronomy. And it looks like the general UV community is moving in 2 directions. One is towards extremely large missions. After all, what we can do is we can do 30 centimeter mirrors maximum in a CubeSat, probably maybe not even 30, maybe 20 centimeter mirrors. So we can only do small mirrors. What they want to do with the next class of UV missions is a 15-meter mirror. So a 15-meter UV mirror in space. Finally, they might come down to a 10-meter mirror. But even so, a 10-meter mirror in space. The JWST mirror is 6 meters. And this will be a $10 billion mission. By the time it flies, which will be 2035 or so, maybe $20 billion. So this is a decadal mission. The other end of the scale is missions that they want to build for about $5 million in CubeSats. And so now there's a CubeSat program that may go up next year, for which they want to spend about $5 million. And because of current technology, you can do the same thing with the CubeSats of $5 million that you could have done with a spacecraft of $100 million of a decade ago. And so this is part of where the future is heading. Now, the final thing is that in India, what has happened now is that space has become a sexy thing. So you have all these universities that want to do space projects, and they all seem to spend about $1 crore to do these space projects, and none of them have done anything to date. The satellite, I don't know of any single Indian university satellite that has actually produced data. And certainly nothing has produced publishable data. And this is what I think is something that we should break. And I don't know if any of you have university contacts, but I think that if we can do this, if we can get this this market, maybe even get 5 universities together and spend 5 crores to build a satellite properly that will do real science, I think that will be a good thing. So I know all of you guys are NewSpace, or some of you are NewSpace guys, and it's always a different thing for me when I talk with entrepreneurs. They tell me, you know, oh, 1 crore, that's nothing. Well, my budget for 3 years is 80 lakhs. And so when Sushmita told me, so I said, what do you need? She said, what do you need? I need 5 crores. Okay, let's talk about it. Here's 5 crores, no problem. But it's not quite so easy. So let me end there. I hope this was, I told NP. NP himself seems to have run off. And so I told him that, that my talk would be rambling and not very focused. So I hope I haven't bored you. Thank you.
Any questions? What applications would you start with? It had to be a university satellite, ballpark.
Well, what I would do, see, I know astronomy. And so what I would, most of these university satellites, they're meant as advertisements. The universities, I see these boards for PISAT-1. PISAT-1 got what, 3 pixels. So they're aimed at advertisements. And I think that if they tried to sell them as here we're doing great science, I think it would work for the university. I think it would work for the students. The university needs it. University needs it for UGC. They get points for all this. And so here is something where it's really a win-win situation. Now the problem with DST funding is, the problem with funding from anywhere, 1 crore is not so hard to get for 3 years. That's what I get. If you want to go, when I went for DST the first time, I had actually gone for 6 crores. And so what they told me was, well, you know, this particular committee can't recommend more than 1 crore. If you want, you can go on to the next committee. But if you want, you cut your budget down to 1 crore and we'll give you the money right now. And so I felt that 1 crore in the hand was better than 5 crores in the ether somewhere. So I said, okay, I'll just take 1 crore. But yes, but this all depends on the pull that people have. You know, this is the real world. If you know Venkaiah Naidu, you can go to Venkaiah Naidu and get MPLAD funds or something. I mean, you know, I don't know. I'm just. I know. There are a lot of funds. There are a lot of funds, and we don't want that much. But I don't know how to get it. So this is what I would say. I would say let's do the best science that we can. These guys at RV College, they had come yesterday for our competition, and they want to do some biology experiment on a spacecraft. And I told them it's not going to do anything. They weren't very happy with me, especially one guy. He said, no, if we don't do, how do we learn? But you got statistics. There have been 10 satellites and 0 have done anything. IIT Kanpur, IIT Bombay, Anna University. Nothing has worked. Why? You're going to do exactly the same thing. You know, what is that? The definition of insanity is doing the same thing over and over and expecting a different result. So I think that if I mean, I'm trying to. Anytime anyone comes and talks to me, I tell them, why don't we work together? You focus on building the satellite. That's not very difficult. It'll teach you a lot. Let us give you the payload. Uh-huh. I think so. I think, but again, universities everywhere, they have a different mindset. The mindset in general in CubeSats is not to do science. It's a demonstration. It's a technology demonstrator. I think in general, anywhere. I think NASA is trying to break this now. And this is actually my biggest, this is the reason I'm a little passionate about this is because I think it's an opportunity cost. I think by being too conservative, by our institutions, by ISRO being too conservative, by our institutions being too conservative, IAA, there's no reason that IAA can't give 5 crores for this. But we're not. We're too conservative to do that. DST, there's no reason that DST can't push this. Instead of that Gavmata stuff or whatever, I mean, push this. So it's an opportunity cost. We're falling behind. We have a chance to be in the forefront. And these universities are wasting that chance. They have the money, they have the manpower, and they're wasting it.
So you worked on the shuttle. So how long before we see it in any country?
The problem with the shuttle was the manned part of it. Orion is coming up. Orion has missed every deadline to date. And so when it will fly, I don't know. If you believe Elon Musk, you'll have manned flight in 2 weeks.
Is going private in the future?
I think that the space agency, there are things that no private company can do. As we found with the Google X Prize, they had thought that they could get to the moon within $30 million. It's not possible. Elon Musk is finding this out. He's getting huge amounts of NASA money, and the research part of it, I think, has to be done by governments. The routine stuff, lofting a communication satellite up, I don't think ISRO should be doing that. I don't think ISRO should be. I think they should subcontract the PSLV business and get out of that. Do the new stuff. Do the human space flight.
Is there any company in India that has the potential to say should outsource?
Well, there had been a lot of interest in when I put in a proposal. ISRO had a call for spacecraft, and I had put in a proposal in about 2007 or so. And because I was used to this American style of getting contractors to do it, I actually managed to tie up with L&T. They were very interested in getting into space, and so I went up and I met all the way up to what's his name, the chief guy, L.M. Nayak, was it? I went all the way up. I met all of them, and they put in a solid proposal, and ISRO was not interested. So I know they were interested. I know this Nagarjuna was interested in building a space construction plant. But what happened is that they went to the chairman. The chairman said, yes, you can do it. And then people down below said, well, I want 1 crore to get this design out. So that's the problem. I think now they're trying, but again, now if you look, all the people who get contracts are friends and relations. Again, I don't know if NP will like me telling this story, but the first time I met him was in Coast in Mysore. And I don't know why he came or how he had heard of me, but he came and talked to me. He caught me and he talked to me. And he said, I'm thinking of, I'm just finishing from this, Erasmus Mundus program, and I want to start up a space company in India. And I told him, I said, it's a good idea, but getting the contracts will be tough. You have to know people in ISRO, you have to know people in DRDO. And I guess he tried many things.
He wasn't nice to them.
He was?
He was not nice to them.
Yeah.
One point, if I may add, US has a good system of having delivery liaison personnel between NASA and subcontractors, tier 1 to 3. We do not have such a system. And I talked to ISRO about this. They're very keen in getting PSLV out and visualizing,
Mm-hmm.
but they don't know how to do it. And within that bureaucratic framework, they have spent last 3 years, in trying to figure that out. Still no results.
Yeah.
And unless you have this mechanism where there is an active, the only reason military personnel are required is because of transfer of technology and the key aspects of it where you don't want confidential from the leak. So once they figure that out, I believe people can do that. Reliance, Tata, Advanced Aerospace Systems.
Goddard Aerospace, yeah.
Yeah, I mean, all of them are pretty good. L&T for that matter, they have built the whole hypersonic turbine PSS.
Yeah.
All of them could do it. It's just ISRO has to figure out how to liaison it.
You know, I don't even think that that's necessary. I think that building a rocket is not that difficult. You'll make mistakes, sure, but it's not that difficult. I bet that if ISRO just gave someone, as NASA has done with Elon Musk, you just give someone a contract for 10 years. You'll get it done. 10 years is too much. You give people a contract for 3 years. They'll do it.
Culture, or is it the lack of the right people in ISRO?
In ISRO.
Is it people or is it the culture?
The people I have worked with in ISRO have been outstanding. I think that what happens is that they get to be conservative. The culture gets to be conservative. And I think it's the same thing. Everyone is afraid to make mistakes. I think that's the main issue. Because if you make a mistake, then you know what might happen. An RTI might come. You wasted $1 million. I mean, we do this, right? We buy equipment, and some of the equipment that we buy we don't use. we thought we wanted it, but it turns out when we got it, we had already moved past it because it takes 6 months to get, or it's not exactly what we wanted. And so people are, we're small people. The amount of money we waste, quote unquote, is small. ISRO, if you're spending 10 crores, maybe people have a right to question how you spend your money.
Would you say the attitude right now towards science missions here is still reactive rather than pushing the boundaries? Because like I heard that the LIGO people were trying for a lot of time until suddenly this boundary happened and
Yes.
and they just got
But they haven't got money yet.
they haven't got the money yet. They got the approval.
They got the Twitters.
They got Ayuka, right?
It's done partly by Ayuka. It's done partly by this ICTS in Bangalore.
I spoke to the ICTS people.
Yeah.
We got like until then we were like it was years we were running missions and then suddenly once we happened then like they got a formal approval but no money.
Yeah, Rahul Narayan. I mean, he met Modi at the Silicon Valley thing, and Modi was very encouraging, but it took them still 2 years after that before they got their launch contract. No, I agree. I think the biggest problem is that the way that a NASA project works is that when they decide at the beginning, this project will be $50 million or $100 million, $150 million, whatever it is. That's the money you get, right? And then you have a contract, so you get so much money at different phases, and you have different reviews at different phases. But once they give you the money, they don't micromanage. And that money is guaranteed. Once you get that money, as long as you meet your phases, you get it. And if you have cost overruns and they are satisfied with your reasoning for your cost overruns, they'll give you the overruns. But I've been seeing the way that that all these big projects work, TMT, LIGO, the money takes forever to come. And when it comes, it still seems to come with strings. If I would compare with the Chinese, I look at the Chinese TMT program. They have they staffed an institute with engineers, and so now when they want to propose for new telescopes, they have engineers there who are doing nothing, who have time to build things. We have not built that infrastructure. We have this we have this tendency to think that we're smarter than everyone else, and so one Indian can do the job of 10 Chinese or Americans or whoever. We also have another problem, which is that we believe in we don't believe in expertise. We believe that that you can take an IAS officer out of here and plug her into here, tax to farming, and there's no expertise involved. They're just good, and we do that in science. So I think that's the differences I see.
So like in some places we have been like exceptionally successful, like the Mars orbiter mission or something.
Yeah, but
Not in terms of science, I don't know in terms of science how much, but then it was considered a pretty like efficient. We were pretty efficient with the costs and everything.
no, but there I think you have to be careful. I mean, I'll tell you what URL said about that. But the thing about the Mars mission, it's a $70 million mission, but we're not doing full cost accounting. In NASA missions, you do full cost accounting. Since 1980, when I joined, when I was an NRC at Goddard, that's when they started doing full cost accounting. So all the civil servants had to start they had to fill out these timesheets for where they were working on. But that was about 1990. So they pay for salaries. In the Mars mission, they didn't account for salaries. Significant part of any mission. The second thing is that when you compare it with the Mars observer, The Mars Observer is a $1 billion mission, but it does science. So U.R. Rao, I was in there for some review, and he came and sat with me for lunch, and he was complaining that none of the Mars experiments did anything. Was it? Really? Really? But they've got some good pictures, right?
After a year, they released really high resolution.
I thought they had.
Yeah, the initial ones. There was some problem they fixed it. I don't know, but
The people on the Viking when.
yeah, and it was again a 15 kg payload. It was a advertisement by
When the Viking spacecraft landed on Mars, they didn't want a camera because cameras don't give you any science. But Carl Sagan said, you'll be sorry if the Martian giraffe walks by and you don't see it. So that's why they had a camera on the Viking mission.
You mentioned about using star cameras.
Uh-huh. Yeah. Well, essentially, that's what a star camera is. It is a telescope. It's a small telescope. So now what we're doing is, we built a 1U, maybe 1.5U. Now we want to go down to a half U. But on the other end, we want to build larger ones. So maybe 2 to 3U. The NASA ones are 6U, and they're talking of doing 12U. And when you do 12U, I don't know if it's a CubeSat anymore, but that's what they're thinking of doing. When you're on the ground, you have all these layers of the atmosphere. So you start with water, nitrogen, ozone. So really you need to be above the ozone layer to do good things. Plus the sky is bright in itself because of all this reflected sunlight. So what we want to do is we want to go outside the atmosphere. Once you go outside the atmosphere, then you're going to do new science anyway. But what we'd like to do is we'd like to go down to about 23rd magnitude, which you can do with a small UV telescope. And again, just stare at places. So now when you stare at places in the UV, you get things that you don't get in the ground. So what you'd like to do is to get a supernova. If you stare at a large enough piece of the sky for long enough, you'll have a supernova there. And so you'd like to get it from immediately after it flashes. So that's the kind of science we'd like.
what is the frequency of balloon launches you conduct from IAE?
We try to do about, we can't do anything now. We're stuck from, I guess, beginning of June to September. We try to do it about every month and a half.
So, if you are suggesting any university student teams already,
Yeah. The trouble with our balloon launches is we're happy to anyone who wants to come and see it. We're happy to have them come and see, but we don't have the manpower to support universities we don't want to become a balloon launching service. We don't have that manpower. It's not our mandate. We want to do our own science with balloons. So that's the main problem. If someone comes to us and says we have something we'd like to launch, if it's possible, we'll do it within our limitations.
my question is, say if university students they're interested in making science out of space,
Yeah.
so you prefer balloons over CubeSats?
Yeah, but because of our own constraints. So we have constraints on the launch. The launch can only be on Sundays between 2 and 4 in the morning because of all the airports around. BIAL, they have so many flights that they only want us to launch at that time. So because of all these constraints, if it were a matter of just saying we can launch any time, then perhaps it would be easier. And then once we launch, then we have to chase the balloon down. And so that's another major undertaking. The students, they chase after the balloon. They start at 2 in the morning as soon as the balloon goes up, and by the time the balloon comes down, it's 5 or 6. So it's a major time investment for us that we don't have the manpower to support. I think it would be a good idea, but we just can't support that.
It's kind of a spin-off to what you're asking, like, so should universities, rather than like going in for these CubeSats like 1 crore missions, would they, if they change their focus to launching balloons, would they have a higher chance of focusing on the actual science than?
What we actually had higher hopes from our balloon program when we started. We thought we would do much better science. It turns out that balloon limitations don't let you do real good science, at least for our small UV payloads. And the other problem is just getting permissions. It's a hassle. But I think that in general, I think that there are good things that they could do with balloons that might if they can go through with the hassle of getting the permissions and all, I think they could do.
Launching balloons like probably plan would maybe also if you go to a remote location, how does that? Or
Again,
airspace is controlled by.
yeah. Again, often what happens is that if no one knows what you're doing, you're okay. I know this is true with drones, where they fly drones in remote areas. So yeah, it might be okay as long as you're far from any air paths. Still better to get permission, and I think it's possible, but it's just there's that initial 1.5 years that you would have to spend.
How detrimental do you think it would be to student satellites if ISRO starts mandating a deorbiting mechanism?
Yeah, I've never been convinced of this deorbiting mechanisms. I mean, they'll come down anyway in a year or two, right? If the low Earth stuff, the small stuff. So I don't know. And you know the deorbiting mechanisms won't work.
Also, ISRO recently has come up with new guidelines for student payloads, where they say that they will provide the bus, and if a student team wants to build something that needs to go to space, they just need to provide the payload. So do you think
That's
is
good.
that a good idea? That'll actually help student teams generate data from their payloads, because they'll have to only concentrate on building that rather than the satellite ones?
The problem is, again, people don't have an understanding of the way science works. You can't just take a bunch of undergraduate students and expect to build a good science payload. You can build a payload. It'll be like the ants on the space station. They send ants up, and so what? Can they build their nests upside down or without gravity? I mean, I don't know. I don't care. So you do a lot of stuff, and I think I would personally I think that most of these colleges are engineering colleges, and most of them would gain more from building the satellite than the payload. I don't think that the payload would you have to worry about so many other things. I think the bus is what they would rather get more building.
Actually, it's counterproductive.
I think so. I think so. I had talked to the chairman about 3 or 4 years ago, and he had this. I wanted to say, if we build something, can we fly it? And he was saying that ISRO wants to have a proposal mechanism where they have developed a bus, where they want to develop a bus for these things. So maybe this is related to that.
No, so ISRO has already come out with these set of guidelines.
Have they? Yeah. So they'll have a proposal mechanism at some point.
Okay. And is it possible for student teams to try and fly their payloads not from India, but like from outside through private contracting?
No, balloons are. I mean, there are a couple of
Actual CubeSat payloads.
CubeSat payloads.
Yeah.
Yeah, we're looking into that. We would we bought our CubeSat from Interorbital, and we paid about $5,000, $10,000, and it seems like for another $3,000 or $4,000 they'll give us a launch. So maybe that's possible.
Yes, it is possible. I think. Hope you know the Astroset is launched by the NASA website. Just now I'm the part of the team. Actually.
Yeah.
It's like a Space Kids India. We have seen like an 18 years team.
Yeah, I saw that. Yeah.
So I'm the part of the mission.
Yeah.
So next mission we have planned in October. It's like Indo-Russian cooperation.
Mhm.
So hopefully I'm Dr. Jayant Murthy invitation. I think
Yeah.
may not to know people, and also Space Generation Advisory Council for National Point of Contact. So just I met Dr. Ahmad Rai sir right now,
Mhm.
like coming.
Yeah.
So just we had a long discussion about Mars analog mission actually. What we are planning in the December 2018 we have planned. So on this behalf of SJC and
Mhm.
so we made wonderful discussion. There is a company doing the cubes in space. I mean that organization offered us free launch services. From usually there are many sounding rockets are available.
Mhm.
So anybody can apply and it can get so many of the companies.
So, but sounding rocket flights will be suborbital.
Yes,
Suborbital.
suborbital up to the Kármán line.
Yeah.
Because ARC also call for the I mean the ideas. I mean they are launching the free launch for this. I mean in the end of the August. Okay. So there will be I think Astrophysics Institute also participating in balloon satellite global. I mean on the 21st of August. I guess. Right there to catch the solar eclipse.
Hmm.
Yeah. I think you made the payload. I guess. So I'm struggling to make complete the payload. So I didn't get the star sensors to capture the things. It's quite difficult. So
Mhm.
I'm still thinking on this.
Yeah.
So $4,000 seems to be rather cheap. Nanoracks charges almost $40,000
Yeah.
for 3 CubeSats.
Yeah.
Where did you get that?
No, that was from when we bought the. This is what my students have been saying, that when we bought it, it was they said that if we pay another 3,000 or 4,000, we can get a launch off their CubeSat. If we can, it's great.
So you'll just give the payload then.
We used their CubeSat. We bought their CubeSat, and for a little extra money. But I agree. I thought it was much more. And for $40,000, I can't afford $40,000.
That's the being the major constraint of flight.
Yeah.
I mean, you can try the nanorods, I think, if possible. Because
Mhm.
Nanoracks
orbital
charges
is-
Nanorax is charging $36,000 to $40,000 depending on.
Yeah.
For
Because
three
maybe you can
CubeSats.
try, I mean, if you are very much serious interested, you can try with an ARC corporation. It's like in New Mexico, there's it's like an aerospike rocket, I mean, just recently they built a completely 3D printed. So maybe you can try, I mean, it's still, I think the applications are open.
But I thought they were all still around this $30,000.
No,
No.
free.
These are free, is it?
Yeah,
Okay.
up to the Kármán line, and also it's like a
So
demonstrator.
these are suborbital flights, and I think the $30,000-$40,000 prices that we are quoting are orbital flights. So that in itself
Okay.
makes a huge difference.
Okay.
Because you can claim first of all heritage for anything that you build for an orbital flight,
Yeah.
which you can't for a
Yeah, no, you're- yeah.
suborbital flight.
Okay. Well, the limitation is with the balloons we use. We buy 2,000 or 3,000 rupee balloons from Pavan, and they're very inconsistent. Everyone says that balloons go up to 100,000 feet. I don't believe that. We get up to 28, 29 kilometers. We've not really. I think we went up to 32 once, but these balloons are so inconsistent. Some of them burst. We had one balloon burst 10 minutes after launch. Identical balloons. So I think that's the main constraint. We in September or in November or December we want to have a flight on one of the TIFR balloons, and those are stitched balloons, and they have gone up to 50 kilometers. So once you go up that high, then you can start doing more science.
Are you having any issues related to the payload stabilization?
We built a pointing mechanism, but that's still heavy. We're limited in weight that we can carry. Our payloads have to be under 5-6 kg. So if you're trying to stabilize a 3 kg telescope, you need a pointing mechanism that's also comparable. Yeah. So we're having troubles with that. We have one now that will probably give us to within about half a degree, which is good enough if you have a wide field of view. We were very naive the first time. We wanted to catch comet Ison And so we tried it with a pointing mechanism. And it was a disaster from start to end. We saw the telescopes going wildly all over the place. This is, you know, they tried this with NGST, with the James Webb Space Telescope. What they thought is that they manage everything out. You do everything on paper first, and if you do everything on paper first, then you save at the end. And because they had so much development built into the JWST, it worked out to be much more expensive.
Sir, where do you see astrophysics and its related science, especially in India, in next 5 years? What are the scopes and uses?
There is increasing pressure on basic research. The government, I mean, not just this government, for the last 10 years, increasingly there's a push to become self-sufficient. And you will see that in increasing fees in universities. IST, the fees are going up. IITs, the fees are going up. So one of the things is you get money. For an institute like us, where we do basic research, we don't have that fund generation capacity. And so it's not entirely clear how important anyone thinks that basic research is worldwide. In India, I think it's a little bit worse, but it's not clear how important anyone thinks basic research is. And so that's going to be a problem, I think. The jobs, there's no shortage of jobs in the country for anyone with a PhD. But having a PhD doesn't mean you're a good scientist.
So what kind of the payload you made for the basic
The space balloon challenge, I don't remember.
I mean,
It was
it's like recently it is an upcoming mission, 31st August.
no, we weren't accepted. We're not going there.
Okay, still,
Yeah.
I'm actually one of the 3 teams. I mean, I have also registered and
Yeah.
also I think as an institute. So still, I mean, I tried to complete the payload completion.
Uh-huh.
You know, I didn't get the sensors and all this.
Oh, I see. Yeah.
It's like
Yeah.
quite difficult. So today I met the chronologist and also.
Mhm.
It's not, there is no help at all.
Any other questions from anyone?
So there is no Indian team.
With respect to patterns you see in science or kind of research that happens in US pre-Trump era, and when you compare it to Indian institutions, the lab costs, laboratories thereof, lab costs, the research mindset thereof, and we had a small discussion on the WhatsApp group as well. What is happening? Basically, what are your views on that? And if you had to pick certain key nuances,
What I tell my students, and they don't believe me, is that the research environment has become significantly more stressful over the last, ever since I finished my PhD, in that because there are fewer jobs than there used to be, there are people who work extremely hard. And we're competing, we have a tendency, I mean, generally, I think we have a tendency to compete against our peers, meaning our neighbors. And our peers are not our neighbors. Our peers are the people sitting at midnight in some campus in Germany or in the US. That I think is the biggest difference that we have. When I look at the student life, I believe that it's too easy, that it doesn't encourage the dedication. I mean, it's unhealthy. It shouldn't be this way. I think we drive people away. I think it's especially hard on women, because many times the early career women are when you have to start making life choices. And in astronomy, that becomes very, very difficult. It's a very unhealthy environment. But this is the reality. The reality is that you just cannot survive unless you put in 60 hours a week. I put in now, I time it. I tried Toggle, so I timed myself with Toggle, and I put in regularly 45 hours a week, and I feel that I work, that I don't put in enough time, and yet I feel I also work harder than any of my students. So they're sitting here, but I think this is the biggest thing. I think that it's a very hard thing to appreciate unless you see people around you who are working till 2 in the morning. These are the benchmarks. These are the benchmarks. Now, these days, students very often have 5 papers before they get their PhD. They've been they get on a major proposal. Very hard to get a faculty position unless you had a Hubble Fellowship or a Chandra Fellowship. So it's much more difficult. In India now, we have a lifeline, which is all the universities. So as long as you have a PhD, you can get a job at a university. We're looking at 30 arc seconds. 30 arc seconds.
Comparatively, what in the market we are getting is 20 days. Comparatively, what is the difference?
It depends on the market you want to hit. If you want to get a 1 arc second, if you want to get a 1/10 of an arc second, then you have to pay so much more. But in those cameras of our class, we're about 1/5 of the price, 20% of the price. Where we've well, no, we say I'm not a commercial organization, and so we don't have that mechanism. If I wanted to commercialize it myself, I would have to find a mechanism to do it. You know, in ISC, it took them 10 years to start commercializing their products, and so I don't want to do that. It's not what I chose to be.
But you all can't do that. This is what your product you're developing.
Yeah.
You can sell it and get yourself into the funding and do more science out of it.
Yes, that would be the goal. That would be nice. Yeah. No, I agree. It's just that I don't want to. I mean, you choose what you want to do. I chose to go into science. I chose not to become a CEO.
But then, is there some like way where you are commercializing, especially the science that you are getting done? Because as we understand that, say for example, even the star sensor that has been developed,
Yeah.
You claim that it's 5 times
Yep.
more cost efficient. It would genuinely be a good opportunity for people who are trying to build things to have that
Yeah,
as
sure.
something that they can
Sure.
buy. So, is there any other way where someone else is commercializing these products, or does that kind of a?
We're looking into ways. The students, maybe some of the students might start doing it once they finish. So we'll look into it. What we do right now, everything we do is out in the open literature. We don't have any secrets. But yes, putting it together is still not trivial. I mean, like Red Hat, right? That's how they make their money. So yeah. So yes, we're looking into ways to do it. But I don't want to do it.
Yeah. So last couple of questions from me. So one of the things that I wanted to understand that as an Indian working in the space industry in US, you also worked on a couple of defense projects, DoD projects. But then that industry is so heavily ITAR regulated where Indians per se cannot get jobs. So was there a cultural divide, or was there some kind of a prejudice that you saw in the community over there while you were working, or was it more welcoming or equally welcoming as over here?
I think ITAR has become a much bigger deal after about 2000. After that, there was that Chinese spy scandal with, who was it? Hughes, was it? Where they were providing, maybe Lockheed. Anyway, they were supplying pointing guidance equipment to the Chinese. After that, that was in 1995, 96. After that, ITAR became much stricter. But also, I was working at a university. At a university, you're not allowed to do classified research. And so, so anything I was doing was okay. Also, ITAR only applies to people who are not green card holders. And so it's fine. But it is a problem now because some of these places, they have science teams tend to be international. But now, if they have international communities, they're not allowed to talk about some things like detectors in open meetings. I've had meetings where I've had presentations.
That would really hamper the process
It
of
does.
development.
It does. It does, and I think it hurts American companies because you get. I was back in 2000. I was trying to get a detector from an American company, and the first thing it was just a lab detector. First thing it went through Department of Commerce, and then the person who was handling it, she had to take maternity leave, and so that file was stuck for 6 months, and then after she came back, it then got transferred over to state. And the guy told me, he said, I know him, so he said, you know, I'm a small company, I just can't deal with this paperwork. Do you mind canceling the order? Cancel the order. I got it from a British company instead, but not as good. A different kind of detector.
So, what do you see is the potential of the Indian space industry ecosystem, right? Even at a startup level, like we see a lot of things happening in US and maybe to some extent even in Europe. You see, India as a country has been enthusiastic towards it, and we see a lot of small companies popping up. Do you see a potential where they'll be able to grow? Is there enough acceptance or critical mass to whatever they need to do?
I think that there are a lot of companies doing a lot of innovative things, and I think those companies will do well. I think if the companies that depend on contracts with ISRO or DRDO, I think those are going to be much more difficult. If you, especially the hardware contracts, those are I think going to be tougher. I think the ways to use a lot of there's a lot of stuff already available, especially the data. If you figure out new ways to do that, I think that those companies will survive. Trying to sell to the Indian space market, I think you have to sell to the international market.
A private space, Indian space market, is that a possibility? Maybe like a SpaceX in India. Like it's first thing is a company having an audacity to do that, but post that, even if there is a company with an audacity to do that, will they be able to do it in our?
You know, I've been involved with Team Indus, not deeply, but I've been involved with them for the last 4 years, and our own balloon program. It just seems like the regulations move slowly. If I see the drone regulations, I think a lot of it, yeah, it seems to me that a lot of it moves slower than the innovation. They don't keep up. But you know, I'm not the right person to ask about that. I don't. I do open research, so I none of the stuff that I do, I don't look to make money. So
no, it's not just about looking to make money, but more happening within the ecosystem, because I think that will, at the end of the day, drive people being able to try and do more science.
yeah, what I would really like to see are some more hackathons. I think especially with Raspberry Pis, and just put them out and let kids work. I'd like to see universities doing that. Yeah.
Anyone else? Anything?
Right.
Thank you guys. I hope you guys enjoyed it. So do come and join us. I think Sir will be speaking.